Unfortunately, the camera shut off at the last portion here. I've already continued, and I'll just fill in what didn't get recorded. What we're looking at, we talked about putting a 2 in here, excuse me, 1 to get f of 1 as 1/4. We're going to look then at putting in a 2 there. And once we put a 2 in here, this will be 2 of those 1/4. Again, it's not 1/8, we're not multiplying, but it's 1/4 times 1/4. It should be 1/16. So we get 1/16 out of that. And lastly, we put a 3, that's going to be 4 to the 3rd, or 1/4 3 times, and that's going to give us 1/64. And then what happens here is we'll go back and say, look, at -3, it should be way up at 64. So I'm going to go here at -3, and way up here, maybe call that 64. And then at -2, it's going to drop down to 16. So I'm going to say -2, maybe call that a 16 down there. And then at -1, it's going to be 4. So -1, I'm going to call that a 4 right in there. And then at 0, you remember that 0, it should be a 1. There's a 1 right there. And then we get into the fractions. At 1, it should be 1/4. So at 1, maybe 1/4 right in there. And then at 2, 1/16, even closer to the x-axis. And then at 3, 1/64, we're getting closer and closer. The larger we get on these numbers, the closer that's going to get to the x-axis. In theory, never touching the x-axis then becomes our asymptote, if you recall from the asymptote section a bit previously. So I connected these dots, the blue dots, purple dots, and we get this green curve. It starts up here very high on the left and proceeds to go down to the x-axis, getting closer and closer and closer, but never touching, asymptotic to the x-axis. Then the author had asked us to find out what the domain and range is, what the x values are. Well, we can put any x you want here. Any x, negative, positive, 0, all those work. So our domain is all real numbers. And I put that in R, that's what I kind of like to use, script R. And the author will probably put this, if this was in the back, say between a negative very large number and a positive very large number. And then how about the y, the range? The range, the y can never get down to 0 because we can never put any number in here for x, which will give us 0 there. So it's always get closer and closer to the x-axis. So we're going to say that y has to always be greater than 0. And that's what I have here. And greater than 0, of course, would look something like this if we had it with the interval notation, something like that. Okay? But not necessarily. The standard notation is very nice. We have 2 others to do here with exponents. The 38 is f of x equals to e to the x. And then we'd like to find f of -3 here. And what I did is just replace the x with a -3. And then the question is, where does e to the -3 come from? Where do I get this number? Well, I get the number here from an e table. And this is the e table that I have in the files for Canvas. These are the packet that I had, a very thick packet, maybe 10 to 12 separate sheets for you, that I was ready to pass out to you before we found that we had no class and I couldn't do it. I still have those packets and haven't made it to give them to you. Yours won't be in pink, it'll be in white there on Canvas. Look for the E table on Canvas, and if you either click on that and bring it up or maybe print it off, either way, you'll find this table. And I'll show you how the table goes and where I get the 0.05 from. If you look at the table, it begins on the left side there with the x, and it goes from x 0.00 all the way down here to 2 on the left. And then in the middle, it starts up again at 2.00 and goes down to 4.00. And then over here, the third column from 4.00 down to 6.00. And then in addition to headings, we have x, and then we have e to the x, and the next one is e to the -x. So both of those tables are very nice for us, both e to the x and e to the -x. For example, if you look at e to the 1, right by where my finger is here, e to the 1.0, you're going to see 2.718. And that number comes from this. To give you a bit of background on e, e is defined to be the limit as x gets very, very large of this fraction right here. In other words, if you keep incrementing very, very small numbers, keep adding 1 plus a very small increment as many times as you like to an x power there, you'll get this number. 2.71828. And we call a natural number here E. It's actually Euler's constant. It's called Euler being a mathematician. We can then either use a calculator to find e to some value or the table. So either the one we found by the table, let's find e to the negative 3, okay? Going through the table again, we'll look at 1 to 0 here, then it begins up at 2.00 down to about the middle of the page here at 3.00. And if you look across the first column there, it says 20.09. That's e to the 3. The next one after that is either the negative 3 or the negative x there, and that's 0.050. I have it in green here, 0.050. And I've erased the initial and final zeros, really don't need those. Basically, 0.05 is a good answer for us. And I compare that to what the author gives in the back. The author gives 0.0498, using a calculator presumably. The 98 there is over 5, so we can round it off to 0.05, which is what the answer we have here from the table. So as you get the table answer 0.05, good enough for us. We don't have to carry it out 4 places the author did. 2 places, very nice. So using the table that you should see in your files there for Canvas, the E table, there are also log tables there too we'll be using a little later, okay? So you need to look at those, be prepared if you want to print them off in advance. Be my guest. We're talking about an exponential on log chapter here, so you will need the log tables. We're not going to be using a calculator. The last section here is a section on, this is 64, it's a little bit after number 38, and the author is asking this. The author is saying, look, 2 to the x is given as 4 for part A. Go ahead and by inspection. We're going to do this later on with a technique, a procedure for doing this. For right now, the author says, look, by inspection, if 2 to the x is 4, tell me what x is. If 2 to the x is 8, tell me what x is. If 2 to the x is 16, tell me what x is. And we're going to try to get each of those answers. There's some more items there. Just go A, B, C, please, and do follow the instructions in the syllabus. In many cases, I've asked you just to try maybe 38A and others there. I just do that. The others get very difficult without a calculator. I've chosen the ones you can do without a calculator, okay? So follow that syllabus if you would. Now let's go and get the answers here, and then we'll talk some more about what's coming after this. If 2 to the x is 4, I think you'll agree that 2 to the second is 4. So x should be 2, shouldn't it? That's a nice easy one. The author is expecting you to do it by inspection, so in this case x should be 2. How about this one? 2 to the x as 8. You should know that's 3. Again, this is not 2 times 3. It's 2 times 2 times 2, which in fact is 8. So in this case, x would be 3. And lastly, 4, and I've kind of done it back here. I've put 4 2's there and multiplied 2 times 2, and then 2 times 2 again. And 4 times 4 is 16. So the answer there should be 4. X should be 4 if 2 to the x is 16. Now, we're going to use this a little bit later in the next session is to say, look, what happens if x isn't 2? Or in fact, let's even do this. Let's say what happens if there's still an x here, we'll leave the x, but we'll change that 4 to a 5. What happens then? Well, obviously x isn't 2 because 2 to the second we just saw was 4, and it isn't 3 because 2 to the third is 8. So this is going to be 2 to the 2 point something, okay? 2 point, and I don't know what it is right here. It has to be more than 2, but it has to be less than 3. The question is, 2 to the what? Not just 2 to the da-da-da, but 2 to the maybe 1.23, or what are the decimals following? At least a couple of decimals to get a bit more accurate than what we have here. And we have techniques for doing that, and that's going to be in the next few sections here. So for right now, the author just asking, look, by inspection, give us that. We're going to use what are called logs or logarithms to find out what, in fact, x is here in the next couple of sessions. So that's what we're leading to in section 17 and session 17 and the others. We're going to talk about logarithms, abbreviated logs. They're a lot of fun, as you saw in the previous video. I want to really get to those because they're so much fun. Logs are exponents. We've talked before about exponents, and the same rules that apply for exponents will apply for logs. And I don't want to get too much into that right now. That's for another session. This is a kind of a short session because this was intended for just before your vacation, so that we would go over the problems from the previous sessions, do a bit here, and then continue after the spring break. At this point, that's all we'll say about session 16. Session 17 will be next. Again, I would really encourage you, if you have some time, I'll try to get these on Canvas as quickly as I can. It requires downloading to YouTube, and then from YouTube downloading to Canvas, getting your URLs to Canvas. So there's a bit of a transition period, it takes a bit of time. But I'm doing that while you're on break. Hopefully maybe at about Thursday or Friday of this break week, you might want to take a look at some of the previous sessions and this one and maybe some of the subsequent ones to get ready. We're getting into with a video conferencing here too at 2:30 every every Monday and Wednesday, I hope, provided that comes out rather nicely. And do follow your syllabus for the exercises. Look at the videos, those should help too. And do have some questions for me. I'm going to use that video conferencing for answering questions to check to see what I can do with that. So we'll try to get everything worked out as nicely as we can, even if we can't see each other in person. But it requires some effort on your part. Put forth that effort. We're halfway through. We can do the rest of this very nicely, I think, together. So this will end session 16 on page 410, 423. We'll be looking forward to session 17 later. Take care.